Hello, my name is Pavel and we continue to explore the temDM MSA package. I'm often asked whether this treatment is applicable to ILS spectrum images only. No, we can also try another example, magical EDX data cube. Download. Save. Wait a little bit. Okay, it's finished. And now go to download and unzip everything. Good, here we have this example. Let's start digital micrograph. Okay, it takes time. Well, these days STEM instruments are mostly equipped with two kinds of spectroscopy. One is electron energy loss spectroscopy, ELS, what we explored in the previous tutorials, and another is energy dispersive X-ray spectroscopy. In Europe it is usually abbreviated as EDX and in America as EDS. Okay, digital micrograph has started. Basically, EDX spectrum images are not very different from ELS ones, but there are a couple of peculiarities. One problem: this plugin is for digital micrograph only, while most of EDX spectrum images are collected with the other software, for instance with Bruker Esprit. For Esprit I have one solution, maybe not very optimal, but it works. Now we go to Esprit. That's how our example looks like in Esprit. We have to do a couple of things in Esprit. First of all, please open map information and read the pixel size. This is 670 picometers. Please remember this value or write it down on the piece of paper. Then we have to save data, but not in native Bruker format, but as a raw data. I showed you the actions in Esprit rather for your information. In fact, we have already everything in the folder we downloaded. So that is native Bruker format and that is raw data. Please note that Bruker produces also some small text file consisting of important information. You cannot read the raw file without this header, so please keep both these files in one folder. Back to digital micrograph and open the tool called import. Well, here in area import Bruker Esprit, click import. We have to find the right folder, magical EDX, and we have to choose to see all files, not only digital micrograph images. Well, now we have to click either on raw file or RPL file, doesn't matter which. Good, import has started. You can monitor the progress in this bar. Now you see the raw number which is currently processed. Well, it takes time because our spectrum image was pretty large. I think it was something like 300 pixels by 200. So it takes time. Here in this output window you see the progress and also the time required to treat each block. Well, now it's finished. We have the imported spectrum image. Unfortunately, calibration was not imported, so we have to calibrate that manually. Remember, we noted some pixel size in Esprit, and now we type it. I prefer to use nanometers, not picometers. And about the energy calibration, I just know that my spectrometer is always 10 eV per channel, and 0 is set at channel 48. Calibrate. Now data cube is calibrated. We can check that. Choose view spectrum, and here there is our spectrum. We look not at one pixel but at many pixels. So you see that data are perfectly calibrated and the 0 is at the right position. Now we close it without saving, and close also import tool. We don't need that anymore. Let's look at the size of image. We need a standard get on tool image status, and we see that our cube is pretty large. It's about 300 by 200 by 2000 elements. So my computer is not so powerful, so I prefer to decrease the size by binning. For that we need a tool called filtering, and here is binning options. Binning by factor 2 in both X and Y directions. Just click start. Binning starts. It also takes time. Here you see the progress. In the meantime, I can say a few words about this filtering tool. In this version it consists of 3 areas. One is binning, which is doing right now, and another is Gaussian filtering, which we explore a little bit later, and the last is just simple averaging. It can quickly generate some average spectrum. It means spectrum averaged over all pixels, or generate so-called average image. It means image averaged over all available energy channels. Good. Now our binning is finished, and here we have a new build image. You see that it is much smaller in special dimensions. So we probably close the original large image and leave only this binned image. Let's store this image. And then I would highly recommend you to apply another pre-treatment. Gaussian filtering of data cube in both X and Y direction. There is a parameter, sigma, and here you see the available range for that parameter. Let's choose just something in the middle of the range, 1.3, and click special Gaussian filtering. So the process starts. Here you see the progress in the progress bar, and also some information in the output window. Yeah, it takes time. Here you see the smoothing in different direction, first in horizontal and vertical directions. Each step takes quite a lot of time. Yeah, but we have to be patient. Why this treatment is recommended? That is because EDX spectrum images are quite sparse. It's great difference from the ELS spectrum images. And this sparsity also very favorite for compressing algorithms. It's nevertheless is not good for multivariate statistical analysis. Well, it's too short time to tell you in details about why it happens and why filtering can improve the situation, I can recommend you, maybe you look at the following articles appeared recently in Micron. So please download this article, and there you will find all details. Now we have just only to know that this filtering would facilitate noticeably the next coming principal component analysis. So here we have the filtered data cube. Let's save it as well. Here it is done. We don't need any more filtering tool. So what has really changed? We can inspect that with a special tool. Click on the old data cube, then on the new one, and then run a tool called Twin View Spectrum. Here we have a plot where there are two spectra from two data cubes plotted as an overlay. So you see that the old data cube, the blue very sparse signal, and the new is red smooth curve. We can also travel along the data cubes. Both markers move synchronously, and we see that this situation is everywhere. To stop this viewing, just close this display without saving. So now we have prepared everything to start principal component analysis. Remember, for that we need a tool, Proceed PCA, and we click Make Matrix. Yeah, there is a prompt. We have to choose the energy region. Maybe we choose not the whole energy region, but just limited one, and treat selected. We don't need this spectrum anymore, just close without saving. In the meantime, the MSA matrix is prepared. Here we are. So now we see already some special information. This is so-called average image. So we can start to extract principal components, and generally we have to extract 10 components at least. But in that particular case, I just know in advance that we will need only 2 components. So let's extract only 2. So extraction starts. Now there is some preparation. Then the first component is extracted. It's done. The second component. Okay, here we are. We have loadings. First loading and second one. And we have the scatter plot. We look at them and close it without saving. Script plot we don't need at all at that case. Now let's run reconstruction. As I said, we need only 2 components. Use both major components. So again, we spend this time by monitoring the progress in the progress bar and also in the output window. We have fun reading which exactly operations right now system is doing. Restore weighting, converting to cube, and so on. It's nearly finished. So we have the reconstruction performed. Yeah, here we have the reconstructed data cube. Let's check what difference the PCA reconstruction did. Click on the filtered data cube and then on the PCA reconstructed data cube, and then run twin view spectrum. Here we have the overlaid spectra. Zoom a little bit. So blue is before PCA and red is after that. We can travel a little bit over the data cube and see that everywhere we have the significant improvement. Well, let's stop it right now by closing the display without saving. We can also test the effect of PCA by another way. In the folder we downloaded, it was a small script, extract maps. This script just extract quite roughly and quickly the silicon and germanium maps. So let's first put in front the data cube before PCA and run this script. We have germanium and silicon maps. And now we put in front the PCA reconstructed data cube and run this script again. So you see how germanium map was improved and also silicon map was improved significantly. Well, at this major note we finish our tutorial today. Please continue to follow the next temDM tutorials.